Alright, this video is all about the wave nature of light. Light comes in two different sort of packages, I guess, in how we interpret and understand it. It can be viewed as a wave, and it can also be viewed as a stream of particles, which we're going to learn about later. And then, in fact, when we do address light, we have to address both of these ideas together. But what we're going to do right now is just go over the idea of light as a wave, which we started to introduce this back in grade 11. So, first of all, let's review very quickly wave mechanics. How do waves work, and what are they, basically? And so last year we learned that waves come in different forms. There is what we call a transverse wave, which looks something like this. And the wave propagates or moves in this direction. But the oscillation that's required to make this oscillation, I'll just put oscillation, is perpendicular to the direction that the wave moves. And so this is called a transverse wave. Remember from last year. You can also have a wave that works a little bit differently. It is a wave that is, sometimes they're called pressure waves, and we draw them by sort of trying to draw these compression, and then not compressed, and then compressed, and not compressed. These waves travel this way. They propagate in a particular direction. But in order to make them, we oscillate back and forth. Maybe I can put arrows there. Oscillation directions on the other one too. And this is called a longitudinal wave. This is like sound waves. Now it turns out that the two kinds of waves are actually just two different versions of each other. So really, we can express all waves as a transverse wave. Waves have certain characteristics. Well, let me go back here and draw another picture. If we take a wave, all waves can be expressed mathematically as a transverse wave, even the longitudinal ones. And so, because light happens to be a transverse wave, we're going to use that model. On a wave like this, there's generally an axis down the middle, which shows the sort of resting position or zero position. And we can label what we call the wavelength. The length of the wave is basically represented by lambda, and it is the distance between two corresponding points on the wave. The easiest places to find wavelengths are the crests and troughs. The distance between two crests or the distance between two troughs. You could also take this point and the corresponding point here, and that would be a wavelength. Right? In fact, you could take any spot. If I pick a spot right here, which is halfway up as the wave is moving this way, I go to the same spot here, and that's a wavelength. The important thing is that all these are the same length. So wavelength is used to describe it basically describes how tight the wave is squished up. Short wavelengths versus long wavelengths. Okay, the other thing that we can draw on our wave, and I'm just going to make more pictures of waves here because, let's draw another one. Make an axis here, and we'll make a wave that goes up and down like this. So if wavelength is sort of the lateral compression and stretch of the wave, then we also have something called the amplitude, which is the height of the crests, A, amplitude, or the depth of the trough. They're symmetrical, right? So on an actual scale, if this is 0, this would be positive A and this would be negative A. The amplitude is sort of the vertical nature of the wave. Low amplitudes have very low bumps, but high amplitudes have very high bumps. Now watch the difference. It's very easy to maybe draw them all to scale. So here are two waves of equal wavelength, but different amplitude. Okay, so here's a wave, and now here's the same wavelength, but different amplitude. If I measure the distance between the crests, it's the same distance between them, the same lambda for both waves. But the amplitude, right, this one is a very small amplitude, whereas this one is a very large amplitude. So it's kind of the up and downiness. You can also do a picture if we draw same amplitude but different wavelengths. Short wavelength, same amplitude, okay? So the amplitude, which is sort of the distance or the height of the crest, you'll see how I tried to draw them pretty much the same height. Whereas the wavelength here, lambda, and then here, much longer. So you just got to get your head around wavelength and amplitude. The other thing, of course, that goes with waves is the idea of frequency. Frequency is the number of vibrations or oscillations. Let's use the word oscillation because that tends to be used more often. It's the number of oscillations in 1 second, or oscillations over time. If we use it per second, the unit is the hertz. So 1 hertz, 1 Hz, is equal to 1 oscillation in 1 second. Units for wavelength, of course, are meters because it's a wavelength, and amplitude as well is usually meters because it's a distance expression. The other thing with a wave is the period, which is equal to the upside down version of the frequency. The symbol for period is usually a capital T because it's a special kind of time. And that just is the time required for one vibration. And of course, its unit is the seconds because it's a measurement of time. I don't use period a whole lot, and in all my experience, it seems that frequency is more often the one that comes up. So we have basically wavelength, frequency, amplitude, and period. And in your textbook, there's a little review of those if you're not sure. So the propagation speed, right, is how the wave moves. It's the rate at which the wave travels along, and that v is equal to the frequency times the wavelength, and this is called the universal wave equation from last year. And we're going to use all these concepts in quite a bit when we start talking about waves. So that's a quick review of the concepts of waves. Waves also require a medium, and the medium for a wave is the thing that's doing the wiggling. So if I go back up to my first picture here, we said that waves oscillate or vibrate back and forth all the way back to here. Well, these oscillations, something has to be moving or oscillating. In the case of sound, we can have molecules of air that are pushing against each other and creating this longitudinal wave. In the case of a transverse wave, you could think of a piece of string being shaken up and down and producing this pattern. But there has to be something that actually does the oscillating or the wiggling. And that, of course, is what we refer to as the medium. Now, how does this all apply to light? So let's go back and look at some of the ideas that we have learned from electricity and magnetism. Because it turns out that light and electricity and magnetism are basically, they have a lot in common anyway. So we remember there was a guy called Ørsted. And Ørsted basically said in very, very simple terms, he said that if you wiggle electricity, right? If you make electric things wiggle around, then what you will produce is magnetism. Now that's a very broad, simple statement. Then we had Faraday, who came along and proved that the opposite was true, that if you wiggle magnetism somehow, by changing the strength of magnetic fields, then guess what? You also can produce electricity. So there was an awareness that these two things were related and that they somehow had something to do with each other. Okay. Then there was a fellow who came along, and his name was Ampere. And what he did is he took Faraday's idea. Actually, sorry, he took Ørsted's idea. Let me rephrase that. He took Ørsted's idea and he kind of defined it a little bit more. So he took the idea of Ørsted in this idea that he basically showed how to quantify, how to measure and get a number for, let's see if I can spell properly today, how to quantify magnetic fields produced by electric current. Okay. So he modified Ørsted's idea. So really, these two guys are the ones that we rely on, because Ampere is sort of a modified version of Ørsted. Okay, now, a new guy comes along, and he takes these ideas, and of course, Faraday, Ampere, Ørsted, they were showing these relationships using mathematical models and by experiment, but they were incomplete. And so along comes this new guy called Maxwell, James Clerk Maxwell. And he decided to take these ideas and look at them a little bit more carefully and to express them a little more mathematically and a little more precisely so that they would be a complete understanding of the relationship between electricity and magnetism. And so Maxwell derived 4 very important equations. The equations themselves are very complex mathematically. They use a language of math that you're not accustomed to yet. But some of you are taking calculus, and some of you have heard some of the terms and some of the ideas. So what we can do is, although we may not understand the actual laws written as they are in math, we can understand them in English, what they sort of stand for. So just for fun, I'll show you what they look like. Maxwell's first little equation is something that looks like this. This is called del. It's not a delta, it's an upside down delta. And it's a del, and it stands for a kind of a complicated derivative taken in 3 different dimensions, x, y, and z. Because life is 3D, so anything that describes real life has to be 3D. So del is sort of our 3D derivative guy. And of course, derivatives are all about rates of change. So this, what I'm writing, if I put E here, and E will stand for the electric field. This is talking about electric fields and how they change in space. So it equals something called rho divided by this little squiggly E. No. Now, these symbols don't matter, and we're not going to use these equations. The little rho is basically something that refers to charge density. So it's telling us something about how the charges are fixed in space, the charges that make electric fields. And this little E guy, he's called the permittivity. We talked about him before. And he basically is a number that describes how easy it is for electric fields to set themselves up in a vacuum. Because remember we said that vacuums are not actually empty. They're devoid of matter, but they do contain what we call virtual particles, which are the things that cause these fields to work. And so there is some resistance to setting up an electric field, and this kind of measures that. So basically, what this side of the equation, this right-hand side, is talking about is it's talking about how electric fields would be set up if you have changes in charge density, or how charge is distributed. So basically, if we wanted to write this in English so we could understand it, we would simply say that electric fields that are produced, they depend basically on the charges that produce them and how they're laid out. They depend on the charges that produce them. That's all. But it's a much more complicated rule. And that's how you can say this simple thing in a way that means it works for all, in the X, the Y, and the Z, in all directions in outer space, and so on. So that's Maxwell's first equation. So you should memorize or just kind of learn or be accustomed to what I'm writing in red. Never mind what's in black. That's just for you to see the complexity of it. Okay? And so remember that the little del guy talks about change. When you see the del, just think about rate of change. Think about derivative. Think about something that's changing constantly. Right? That's what it means. Now you notice there's a dot because that's the certain kind of multiplication for vectors called the dot product, which you calculus people know, but the rest of you don't. And you'll learn that probably very soon. So it's just a kind of multiplication. Just think of it like that. Then we said, okay, well, we also have del dot B, which deals with a magnetic field. And this happens very simple. It's 0. And so what does this mean? Well, in English, what this is basically saying is that there are no magnetic monopoles. Remember we talked about that. You can't get a north or a south pole of a magnet alone. In other words, magnetic fields are continuous. That's another way of saying it. And so these two first things, these two first rules, are important because they set up the nature of these two things. So when you, Okay, now, to get a little more complicated as we go on, next we talk about a different kind of multiplying called the cross product, which is written like this. In the electric field, if you do the same operation in a cross way, you get this weird thing. Now, these are some new symbols as well, which you've never heard of, but I'll explain them and you'll say, okay, I kind of get the idea. These little funny, they look like 2's, but they're not. This little symbol here is really just a version of, when you write, for those of you in calculus, you write dy by dx. Well, this is a funny looking d, and it's a d that basically means take a derivative. So it again indicates find out how something is changing. So when you see this b, it means take a derivative, but it's called a partial derivative, and it's basically done by taking the derivative of one variable while all the other variables are constant. You just pretend they're all not changing because it's too complex, right? So it's a mathematical trick, but it really still means changing. It's all about changing. So when you see this this partial derivative on the right-hand side of the magnetic field right here compared to time, this is just an expression that tells us how magnetic fields are changing with time. Okay? And what this means in English is it's basically Faraday's idea. He restated Faraday's principle. And it basically means that if you change a magnetic field, see on the right-hand side, the B and the T is a changing magnetic field, that will produce electric fields. So changing magnetic fields produces electric fields. Okay? If you go on in physics, you'll study these equations probably in your second year. But for now, we just want to know what they mean. So changing magnetic fields produces electric fields. So there's that one. And there's one more, and it's the most complicated of them all. The last one has to do with what happens if you do the cross product of del on a magnetic field B. And it produces this crazy equation which looks like this. It's a mu with a little naught, and then there's a j, and then they have all these mathematical symbols. This little guy comes back again, and then another derivative here, partial derivative of how the electric field is changing over time. So again, this little guy is the permittivity, and it tells us how easy it is for electric fields to form. So if you ever see permittivity. This other guy over here, he's called permeability. And we saw him already, permeability, because when we were doing magnetic fields, remember how mu popped up, and he has to do with how easy it is for magnetic fields to form. So these are just constants that describe how these things form. And you'll notice that the two key things for us are, this talks about how magnetic fields are changing, whereas this part talks about how electric fields are changing. And so in English, we could write this. This is actually a modification of Ampere's law. Ampere, what Maxwell did is he expanded on Ampere's original law, which talked about the magnetic field strength around conductors, around, he took Ørsted. Remember I said he took Ørsted and he made it mathematical, and he expanded on it. This basically says that changing electric fields produce magnetic fields, or electric current. I'm going to write it like this. Changing magnetic fields. Whoops, wait a minute. Sorry, electric fields, we better get that right. This is the backwards one, because this is Ørsted originally. Changing electric fields, or moving charge, or wiggling charge around in any way, produces magnetic fields. So you can see how the concepts are what we've been talking about all along. They're just put together in these complicated equations that describe them mathematically. The ultimate thing that we need to derive from this, or the ultimate idea we need to get, is the idea that electricity makes magnetism, and magnetism, makes electricity. Magnetism makes electricity, and electricity makes magnetism. Okay? In particular, we should write changing. Changing magnetism makes changing electricity, or current. And current, or changing electricity, makes changing magnetism. And that is the secret to what Maxwell finally put it all together and discovered, or iterated, was that light itself is a propagation of a wave that is made up of these two things. So what he said is that if you have electricity and magnetism wiggling and one makes the other, you set up an interesting picture, which I will try to reproduce for you here. And it's a picture I think we may have seen. It's a 3D picture, so it's hard to draw, so I'll use colors. Here is a vibration, and this vibration will represent wiggling electricity. So if you take charge and you basically wiggle it up and down, what it does is it produces ripples like this that propagate outward from that charge. But we don't necessarily see these kinds of things. These ripples, it's like dropping a stone in a pond, right? So if I have some water here, let's say I'm looking downwards on this lake, and I drop a stone right there, and it goes clunk, and then it goes, little ripples begin to go outward, right? If I turn this up on its side view, so I'm looking at the water flat, then these little ripples would look like this as they rippled out. And each one of these black lines would be the crest of one of these ripples. And so this, what I've drawn, is exactly what happens, except it's not in water. It's in the electromagnetic field, which is a non-material medium. That's why it was so hard to detect. I think we talked about that last year. It's a non-material medium, but it permeates everything. It's all around us, and these ripples ripple outward. Now here's in green, I'm going to try to draw another weird-looking thing, which is going to look something like this. Now, in order to make the perspective jump out, I'm going to add some lines, which really have nothing to do with the picture, but they just give us perspective. So I'm going to draw these lines straight up and down so we can see that this blue wave is vibrating in the up and down plane. Okay? Now, the green one is vibrating as well, but it's vibrating sort of in a 3D way in and out of the board. And so these little lines will help give that impression. Whoops, and I missed these guys. So what we're trying to show here is how the green is in and out of the board and the blue is up and down the board. The blue represents the vibration of electricity. And the green represents the vibration of the magnetic field. So the electric field and the magnetic field. And what's important for you to remember is that one causes the other. So, as this electric field begins to move, it automatically produces this magnetic field that wiggles with it in the same way. But the magnetic field also then produces the electric field that wiggles with it in the same way. So it's kind of like a self-reinforcing thing, where the magnetic wiggling produces the electric wiggling, right? The electric wiggling produces the magnetic wiggling, because we have the two principles of Oersted or Ampere and Faraday working together. And this is what Maxwell realized, that it would be possible for a wave to exist where these two things balanced each other out, reinforced each other, and self-propagated. So this wave is self-propagating. It moves along through the electromagnetic field. Now, what is this wave called? Well, it's called light. This is what light is. However, it's actually called electromagnetic radiation. And light is only a small part of it, because now we've learned that there are different size waves. So if I take that same picture and I draw it like this, okay? And for simplicity, I don't put the green one in. We just imagine that it's there. Then we just think of this as a light wave. But we always have to remember there's also that green wave going along, wiggling with it. Maybe I'll add it here just for this one. So there's always that green wave that kind of going like that. See, it makes it look funny, so I'll erase that. It's very hard to draw this. So we just draw one wiggle, but we know there's two wiggles. It turns out that you can have all the wave properties, like amplitude and period and frequency and wavelength, apply to this. So you can have wavelengths that wiggle like this, or you can have wavelengths that wiggle like this, and they can be all different wiggles. And we discovered that all these different wiggles actually produce different effects. The very same phenomenon, right? If we have big long wiggles, where the wiggles are very wide, sometimes kilometers long, or at least tens to hundreds of meters long, we get what are called radial waves. And we use these to communicate. Radial waves can be used to communicate. If you make them a little bit shorter, but not too much shorter. Now, to draw this to scale is impossible. In fact, these waves would actually be much shorter. They would be on the centimeter size between crests, but then I'm going to be able to draw the rest. So this is not to scale, but these are called microwaves. And I think we might have talked about this picture last year. Then a little shorter still produces a new kind of wave called infrared. And this is how heat radiates through space or through a vacuum. And then we get an interesting phenomenon where we get short waves, shorter still. And these ones can be detected by our eyes, and so we have red light. And then we have orange. Whoops, orange would be a little shorter still. Let me go back to that. It's hard to draw them getting shorter and shorter and shorter. So anyway, the distance between the crests would be even shorter. Then we have red, orange, and then we have yellow, shorter still. Orange, yellow, and then we have green, shorter still. And this is the only difference between what we see as green and what we see as yellow, the shortness of the wavelengths. And then blue. And of course, red, orange, yellow, green, blue. And of course, we have violet as well, but just to save space, I'm going to just leave it at that. And then what happens is if they get any shorter, we stop seeing them altogether. We can't see these ones, they're too short. But these little short ones here, which are even shorter than blue, are called ultraviolet. These give us a sunburn. And then if they get shorter still, these are called X-rays. And then shorter still, which produces a very tight little wave here, we would have something called gamma rays. And then lastly, they can keep getting shorter and shorter and shorter, but we stop giving them names. Anything shorter than this, and I'll just draw it partially down because it's too hard to draw, these are just called cosmic rays. Okay? Now here's the interesting thing we also know about waves. I'll just move this up a bit. If I take the spectrum, what I see is as I move this way along the spectrum towards this end, the wavelength gets shorter or smaller. As the wavelength gets shorter, I'll draw another arrow here, the energy increases, the energy that's in the wave. All waves have energy because they're wiggling, they're motion, right? They represent energy. But interestingly enough, it's the wavelength that determines the energy. And we're going to study that actually. We're going to look at Einstein and some of the things that people have done to prove that or to demonstrate that. So that means that as you get to the left of this picture, your energy increases. And so the amount of energy in cosmic rays is a lot more than there is in radio waves. That's why radio waves don't seem to hurt us when they go through our bodies and they are all around us. Yes, FM is everywhere. And microwaves are also coming out of our cell phones all around us, and they don't seem to hurt us. You can, in a closed space, use microwaves to excite water molecules and heat things up and cook food, but that doesn't happen to people because we're not exposed to the same power of microwaves from telecommunications. However, there may be some research that shows that, they might be causing some damage over the long term. Infrared is when you feel the heat of something from a distance. If you're standing by a campfire and you can feel the heat. Heat can travel in different ways. It can travel through convection and conduction, but it also travels by radiation, and that's how the sun's heat gets to us through space. The next waves are also energy, but our eyes have special cells that are able to see them. We can't see the ones I've drawn in black, but we can see the colors of the spectrum. Blue light has more energy than red light. And then further on down, we have ultraviolet, which has more energy still. Incidentally, I'll just go to the bottom. If we look at the spectrum and we look at the ultraviolet section, which I'll start here, if you go past here, the amount of energy that the waves have is enough that it can actually ionize molecules. So we call this ionizing radiation. Red, blue light, microwaves, they don't seem to do this. They don't seem to knock electrons out of their energy levels in atoms. Now, ionizing is a bad thing if these molecules or electrons are in your body and you knock the electrons around and you mess up the molecules. This can cause severe damage, and these kinds of radiations can kill us. Ultraviolet gives us skin cancer. X-rays, we can look through our bodies with X-rays because they have so much energy, they pass right through soft tissue, but they can cause damage. Gamma rays, we get gamma rays from nuclear reactions, nuclear bombs, nuclear explosions, terrible things that cause damage. And cosmic rays come from really weird astronomical activities like supernova explosion and so on. And of course, cosmic rays would wipe us out pretty quickly too. So of course, as living creatures, we avoid radiation. Now luckily, we have a shield around the Earth, because all of this stuff is out there, but there's a shield around the Earth called the ozone layer, and ozone is a molecule of O3 that when hit by radiation turns into O2, and then when that gets hit by radiation it turns back into O3, and it bounces back and forth and it sucks up the energy and it protects us from most of these dangerous rays. Basically just a little bit of ultraviolet gets through. So that's how we're able to live. Without that ozone layer, it would be very difficult for life to form. So all of these are examples of electromagnetic radiation or light, which is a wave, right? So light. So when we use the word light now in physics, we have to think that it means all those things, not just light you can see. So light, or more properly, electromagnetic radiation, is a wave. It's a double wave in 2 dimensions. Radiation. It's a double wave in 2 dimensions that is an electric portion and a magnetic portion, and the electric portion induces or causes the magnetic portion to exist, and the magnetic portion causes the electric portion to exist, and so the 2 of them interact with each other and make a self-propagating wave that travels through space, and this is what Maxwell was able to discover, and it launched us into the modern age of physics. And that's as far as we will go on that today.